Hello, welcome to the class of complex analysis. This is a second semester class. So, analysis, complex analysis. And in this class, we're going to use the textbook. Textbook is Conway's. John B. Conway. It's author. The book is Functions of One Complex Variable, second edition. Okay, so this is a textbook. For this class, we will have 3 hours lecture a week. Because so far we don't, we have online class, we don't meet, so we decided to present 3 hours lectures one time on Tuesday, and then you have a week to watch them and understand the material. Okay, so I will leave some exercise randomly. I'm not going to leave it every class randomly. I will give you some exercise and you can try it, and if you have a question, send email, ask me. And for this class, we will have midterm exam and the final exam. Okay, the midterm exam, final exam. The dates we will determine it later. And the midterm and the final exam are 50-50 for your final grade. Okay, so for the final grade, if you have 85 and above, it is A. 75 to 84, that is B. 65 to 74, C. 60 to 64, D. And below 60 is F. Okay. Okay. So for the midterm and the final exam, I will select some problems either directly from the textbook or from the recommended exercise, and you do it in the required time. So there is no new problem in the exams. The exams are used just to check your study, not your creative idea. So if you understand all the material in the textbook and you know how to do the exercise, then you should get a good exam grade. Okay. Anything else? Yes. If you have any question, you send me email. You send me email. We will discuss that question, or maybe I will present. I will make a separate video to discuss this question to everybody. And for the exam, we have the following format. The exam possibly will be from 5 to 7 or 5 to 7:30, some like that. And during the exam, you're going to have a camera and a microphone. You have turn on the camera, turn on the microphone so that I can see you. I will send you the Google Meet link so that I can see you through the webcam. I can hear you through the microphone. Okay, and you have the exam will send it to you like 10 minutes before the time. Like for example, if your exam is from 5 to 7:30, you will get I mean, say if you will get the PDF file, you will get the exam at 4:50, and you need to turn in your exam no later than 8. Okay, so 5 to 7, no later than 8. I gave you extra time for the technical problem. And I don't need you to print out the exam. You only need to label the problem number correctly and take photos or scan your answers and send that to me. That's enough. Okay, so you don't have to print. It's not necessary to have a printer in your room. Okay, so that is for the exam. Okay, so now let's start our class. We will have the class. This is the second semester of complex analysis. Let me briefly discuss refresh or review what you have to know from the first semester. So in the first semester, we discussed the chapter 3, 4, and 5, basically. Chapter 3, you have the power series and the analytic functions. Okay, so you have power series and you have analytic functions. And also in chapter 3, we study a special type of analytic functions, Mobius transformation. Okay, Mobius transformation is a rational function, az plus b over cz plus d with some ad minus bc not equal to 0, some conditions, whatever. So if you don't remember some facts, just go back and review it. And also analytic function is a power series. Power series is analytic functions. For the power series, you have radius convergence. How do you find the radius convergence? You have the lim sup stuff. Okay, so that is chapter 3. And then you have chapter 4. Chapter 4 is complex integration. Integration, I bet. Integration. Complex integration, by definition, is almost identical to the real calculus integration, but you have to have the Riemann-Stieltjes integral. Remember that. What is a Riemann-Stieltjes integral? Stieltjes. Riemann-Stieltjes integral. The dz, you have to understand dz. And also we know the zeros of analytic functions and the index of closed curves and the Cauchy theorem and the integral formula. The important thing is a Cauchy theorem and integral formula. So you have several versions of a Cauchy theorem and several versions of an integral formula, and also in this part you study the homotopy. So this moment I just try to review some important concept. If you are not very familiar with those concepts, it means you have to spend time to check those corresponding sections. Okay, and then you have the how to count the zeros, how to get the open mapping theorem. Zeros, open, O-P-E-N, open mapping theorem. Open mapping theorem. And then you have the simple connectivity. And after that, you have the one of the important Gauss-Seitz theorem. Gauss-Seitz theorem means if you have the integral always 0 over the triangular path, then the function is analytic. Remember that. Okay, and that's more or less the chapter 4. And chapter 5, you study the singularity. What is a singularity? Singularity basically just means you have infinity. Okay, if it's not infinity, it will be essential singularity. That will be a disaster. So in most cases, we study the removable singularity, the pole, infinity, and the essential singularity, nothing. Okay, removable means it's still very good. Pole means it's not a number, but it's infinity. Essential singularity just means it can be very, very random, chaos. Okay, so you have singularity. And after that, when we talk about singularity, we have the residue, the integral stuff, and the argument principle. Okay, so those are the basic and important concept. You just read it from the table of contents, you will see them. If you can review or recall some facts, then it means you have a good memory. If you don't, not a good memory, you have a good background. If you don't understand what I'm saying, you need to review the corresponding section. Okay, so this semester we're going to start from chapter 6. Chapter 6 is a maximum modulus theorem. The maximum modulus theorem. Let's move to the page. Okay, so now let's start our class. The first section, chapter 6, section 1, the maximum principle. The maximum principle. Okay, so let's start from a simple observation. Let omega be a subset of complex plane, and suppose that alpha is in the interior part of the omega. When we say a point in the interior part, it just means there is a number, a positive number, rho, such that, when we say positive, of course it's real, such that the open disk centered at alpha with radius rho is totally contained in this subset. Okay, so we don't say subset is open. Of course, if subset is open, every point is an interior point. If subset is not open, we only consider the interior point with this property. All right. Okay, so let's see. You have, this is complex plane. Have alpha, whatever position, it doesn't matter which quadrant it is. This is the radius rho. Okay, so what is modulus? The modulus of alpha is this. The modulus. Alright? And you will see here, this is open disk. You extend it. So definitely you can find a point cosine. So that the length of cosine is greater than the length of alpha. Is a distance between the origin and alpha. And then we extend the ray from the origin to alpha. We can get a point cosine in this B alpha rho. It's obvious because you have an open disk. Have an open disk, you can definitely have. It's not more. It is more than one such cosine. Okay. With this, then we have what? The length of cosine is greater than the length of alpha. Right? That's a very obvious geometric observation. Okay, so we're going to use this geometric observation to prove the maximum modulus theorem. Maximum modulus theorem. Okay, so whenever, let's restate it. Whenever you have an interior point, you can always find a cosine so that cosine belongs to omega and the norm of cosine is greater than the norm of alpha. Okay, so alpha is interior, always exists cosine in omega, because you see cosine is inside this open disk. Open disk is in omega, such that norm cosine is greater than norm alpha. Okay, so if we do not want this happen, we get the equivalent statement. If for alpha in omega there is no cosine in omega such that cosine is greater than alpha, which means alpha has maximum modulus. Okay, no cosine. No, there's no cosine. This condition is negative. You get a negative result of this conclusion. If this happens, then alpha is not interior. Right? Alpha is not interior. Not interior. This is equivalent to say alpha is on the boundary. Okay, so let's recall the theory behind it. You have statement A and statement B. A implies B. It is equivalent to say no B will imply no A, or not B imply not A. The negative statement B will imply the negative statement A. These two statements are equivalent. Okay, so we just use this result. And another thing is from the topology. Any set is the union of the interior part and the boundary. Any set is going to be the union of the interior part and the boundary. Outside is the exterior part. Inside is interior part together with the boundary. So here it's not interior part, it has to be on the boundary. Okay? So that's a topology. What is the, okay, so the interior, alpha is interior of X if there exists r greater than 0 such that the ball centered at alpha with radius r is completely inside X. That's interior. Boundary point is a boundary point of X if for all r greater than 0 the ball centered at alpha with radius r intersect X is not empty, and the same ball centered at the complement of a set is also not boundary, right? So it contains some point from the set. It also contains a point from outside the set. Always, if this always happens, this is a boundary point. Okay, so every set is a union of interior plus and the boundary. Okay, now let's study the maximum modulus theorem. Maximum modulus theorem, the first version. The first version says the following: if F is analytic, in a region G and a point A is a point in G with ops value of f of A is greater than or equal to ops value of f of Z for all Z in G, then F must be a constant. F must be a constant. All right. Okay, so let's try to prove it. Proof. First, we denote the image of G under F. Omega is F of G. And we let alpha be the image of A under F. Alpha is equal to F of A. Then, from the hypothesis, from this statement, we have that the alpha is greater than or equal to the modulus of alpha is greater than or equal to the modulus of cos for all cos in this omega. Okay, if this all can happen here, this one, if this happens, then alpha is in the boundary of omega intersect omega. Okay, it is a boundary point, and it is a point inside omega, so it's in the intersection. But if this happens, this implies that omega is not open. Whenever your set contains a boundary point, it's never open because that boundary point is not the interior part. Okay? Omega is not open, but we know that region is open connected here, region. So G is open, then the image of G under an analytic function is also open. So the open mapping theorem tells us omega is open. Okay? Then or f is constant. If f is constant, of course its image is not open. When f is not constant, then the image will be open for the analytic function. Okay, either omega is open or f is constant. Here it's not open, that implies f is a constant function. It's a constant function. Okay, so you see here we prove it, but this proof depends on this open mapping theorem. All right. Okay, so this is the first version of a maximum modulus theorem. Now let's see how do we state this theorem in a different way. The second version of a maximum modular theorem. Okay, so let G be a bounded open set in the complex plane. And suppose F is a continuous function on the closure of G, which is analytic inside the G. Okay, then we can have the maximum of the ops value of f of z. Z belongs to the G bar, the closure. It is equal to the maximum of the modulus of f of z. Z belongs to the boundary of G. They belong to the boundary of G. Okay, so f is a continuous function over the G bar. Then ops value of f is also a continuous function over the G bar. The G is bounded, G bar is also bounded. And bounded closed set is a compact set. So the maximum modulus function is bounded over the compact set. So that's actually that is the reason we put bounded open set. In the first part we don't put bounded. In the second part, because we want to discuss a maximum or minimum value, we don't want infinity. If there's no compact set, we have no idea if this maximum is infinity or not, right? So that's the reason we need to add this boundedness. We want to compare two concrete numbers instead of infinity. Okay, now let's see how do we prove it. Okay, so G is bounded. Then there is a point A in the closure of G such that f of A is greater than or equal to upper value of f of z for all z in the closure of G. How do we get it? So basically we have the following thing. G is bounded, then you start from this this part, any interior part you will not receive. You will always have this you will always have another psi greater with a modulus greater than alpha. And this moment, where yeah, this moment because you find a point G. Well, let me hold on a second. Okay. Let me make this clear this way. So G is bounded. This implies G bar is bounded. Closed. So it is equivalent to G bar is compact. Then upper value of f of z is continuous over a compact set G bar. Upper value of f of z is continuous over compact set G bar. Then this implies the compact set has a compact image under continuous function. So f of z, f of g is also a compact set. F of g is also a compact set. Alright? So f of g is compact set. It is bounded and closed. F of g is bounded and closed. You see, you have a bounded closed set, and you use circles to enclose it. Use a minimum circle to enclose it. Then definitely some moment, the first moment, this circle will touch the set and also surround this whole set. And this point corresponds to some f of a, and its a belongs to the G bar. So use the circles to surround f of g. Shrink, 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 shrink. Shrink the circle, and at certain moment the circle will intersect f of g and still surround f of g. Okay, you just like use a rubber band to shrink it. And the intersection is f of a for some A in G. Yeah, this is right, the argument. It's a right argument. Okay, so you always find a point A on the closure such that f of A has a maximum value. Okay, and then let's see, if so we have two situations. If f is a constant function, if f is a constant function, then the statement is a maximum over the maximum of upper value of f of z over g bar is equal to maximum upper value of f of z over boundary of g. The conclusion is true trivially. Okay, it's always constant, nothing changes. If f is not constant, if f is not constant, then we will see that by theorem 1.1, this point A, where's A? Where's A? Here, this point A cannot be an interior point. If A is an interior point, then f is a constant, right? A cannot be an interior point. A is a boundary point. A belongs to the boundary of G. A belongs to the boundary of G, of course, the conclusion holds, right? So we're trying to push Z to the, A to the boundary when f is not a constant. Okay, so that's the situation, the proof of second. Okay, in the final part of the proof, when we say f is not constant, then by theorem 1.1, A cannot be an interior point. But theorem 1.1 requires connectedness. Here, we only assume this second, where's the second? Yeah, the second version of a maximum modular theorem. We only require a bounded open set. So how do we go through this point? So we can say we choose a connected component containing A. We choose a connecting component containing A, and this is a connected set. And if A is the interior point, then you will get the contradiction. Okay? So if it's not connected, you will focus on the component. All right? And then next, let's see how we do it if we don't have boundedness. So the boundedness is very important when we try to do it. We guarantee that f of A is a finite number. Okay? So let's see an example. Let G be a region, a band, x plus iy. Here, y is between negative half 2 and positive half 2. It says it's horizontal band, infinite horizontal band. Okay, then define f of z as a e to e to z, e to e to z. Then clearly f is continuous over the closure of G and analytic over G. It's exponential function. Exponential function is a perfect function. It's analytic everywhere. All right. Then we pick up a point. This set does not include the boundary, but we can choose a point from the boundary. So let Z be in the boundary. Z be in the boundary, then Z is x plus or minus 2 pi I. It is either positive 2 pi or negative 2 pi. Then exponential of Z e to x and e to plus or minus 2 pi I, 1/2 pi I, not 2 pi, my bad, 1/2 pi I. Then e to plus or minus 1/2 pi I is plus or minus what? Plus or minus of I, right? So it's equal to, let me copy it here, to x e to plus or minus 2 pi I is I plus or minus ex. Remember, e to I theta is cosine theta plus I sine theta. So cosine plus minus 1/2 pi is 0. Sine plus or minus 1/2 pi is a plus minus I, so we get plus minus I. And then f of z is e to z is e to plus minus I e to x. E to plus minus I e to x, absolute value of z, f of z is always equal to 1. E to I theta, when theta is real, is always 1, right? The modulus is always 1. So what we know? We know that the modulus of f of z is constant 1 for all z from the boundary. All z from the boundary. All right? So this is one thing. What happens if we do not choose point from the boundary? We let z be x. So we choose a point from this x-axis. We let z be x, then f of x is e to x. It will approach positive infinity as x approaches positive infinity. E to x becomes bigger and bigger. E to x also becomes bigger and bigger. So the maximum of f of z between negative 1/2 pi I, sorry, not y between negative 1/2 pi and positive 1/2 pi I, and the closure is infinity, but the maximum of the absolute value of f of z over the boundary y is equal to 1/2, and then plus or minus 1/2 pi I is constant 1. So they are not equal to each other. Okay? So this example does not contradict to the maximum modulus. Contradict the maximum modulus. Theorem. It's solo because in our theorem we require the function, we require the region to be bounded, because here G is unbounded. For the unbounded set, actually that A does not exist. Remember, in the proof we first locate a A. because of abundantness, you can use circles to cover it, and then you shrink the circle, you will find A. This place is unbounded, its image is unbounded, so there's no way to find such A. So the proof does not pass. Okay, so if we want to drop the boundedness, we need to control something, because you see here, when you pick up a point along the x-axis, you will approach infinity. If we want to control this phenomena, we will have the following stuff. Okay, so you see the definition 1.3. Okay, so the definition, if f from G to R and A is in the closure of G, or A is infinity, then the limit supremum, superior, the limit superior, lim sup of f of z as z approaches A, denoted by lim sup z approach A f of z. This is notation. Is defined by the lim sup f of z approach A is the limit, the supremum f of z belongs to G, intersect the ball centered at A with radius R. Here, R approaches 0 plus. Okay, that's a lim sup. So when you have a set G, you have a point A, then you just choose the smaller disk and pick up the supremum of this value f of z. Remember, we are talking about a positive number, real function. Real function, you have a supremum. You don't. If it's a complex function, there's no supremum of f of z. Okay, we just get the supremum of f of z, and eventually you shrink this r. It will approach to f of A. I mean, by the geometry, it looks like. So that is defined to be the lim sup of f. Okay. It studied the behavior of the supremum. And similarly, the lim inferior, the limit inferior of f of z as z approaches A, denoted by lim inf z approach A f of z is defined by lim inf z approach A f of z is equal to the limit r approaches 0 plus infimum of f of z belong to G, intersect the ball centered at A with radius r. You just change the supremum to be the infimum, you will get a lim inferior. Okay, and you can see that the limit of f of z exists if and only if lim sup f of z is equal to the lim inf f of z. They both exist. Okay, equal to each other, then you will have the limit. It's like the a weak version. It's like the right limit and left limit, but it's from top and bottom. Okay. And now let's see what is an extended boundary. Let G be a subset of C, then let the boundary infinity of G denote the boundary of G in C infinity, and call it the extended boundary. Extended boundary of G. Okay. Extended boundary of G is not very mysterious. If G is bounded, then the regular boundary of G is the extended boundary of G. If G is unbounded, then the extended boundary of G is the boundary of G just union infinity. So for example, this one, what is the regular boundary? Regular boundary is the top horizontal line and the bottom horizontal line. But in the extended complex plane, you have to add infinity. So it's just a original boundary join the infinity. Okay? So with all these preparations, we can discuss the so-called the third version of the maximum modulus when we do not have boundedness. Okay, so this video will stop. We will start. We will discuss the third version of a maximum modulus theorem in the next video. Okay. Okay. I stop it here. Thank you.